So let us, without further ado, start with the first element in this setting. The abstract sample space corresponds to the performance of a chance experiment. Now, we should either be able to perform such an experiment or at least conceive of it being performed. This results then in a Gedanken chance experiment, a thought experiment, something that can be conceived of. And the moment one performs such an experiment, one gets outcomes. The idealized outcomes of this chance experiment are called the sample points of the experiment. The idea being that, if from a purely visceral point of view, one is performing an experiment like throwing a die, tossing a coin. And the moment you do this, we are inheriting, acquiring an outcome, an idealized outcome, by sampling randomly from the possibilities for the outcomes. And hence, we call the possible outcomes in this formal setting sample points. And together, the collection of all conceivable sample points forms a rich collection of elements, a set of elements. This set we will then call the sample space. The notion that identifying the family of events precisely and carefully, surprisingly, was relatively new. The idea is due to Robert von Mises and only came to fruition around the end of the first quarter of the 20th century. But around that time it became clear we have to codify exactly what the objects are under discussion. The awakening of probabilistic interest in the 17th century, during the Renaissance and thereafter, saw results emerging and a theory in nexus slowly emerging from the foam, as it were. But the theory was not well formed. What we had obtained through the 17th, 18th, and even through the 19th centuries, with a gradual quickening of results, as is the case in much of science, we find a scattershot set of results without any formal fabric knitting everything together. What is the worth of a formal theory? Well, the ultimate worth of a formal theory is in the richness of the predictions it provides and the verifiability of those predictions in commonplace settings. In this, of course, the theory of probability has been wildly, surpassingly successful. So, here's where we begin. Identifying, codifying, following von Mises, the collection of all idealized outcomes, the sample points of the experiment. Some notation will lubricate the wheels. So, let's, without further ado, talk about idealized sample points of the experiment, generic sample points, typical sample points, and identify them by the lowercase Greek letter omega. Now, omega now represents a generic, typical, if you wish, outcome of an idealized experiment, a sample point. The collection of all possible, conceivable sample points forms this potentially very rich space of possibilities. This is called the sample space, and we inevitably use the uppercase Greek letter omega to represent this. Now, this is standard traditional notation over the last century, but we will not adhere slavishly to this kind of notational convention. If, for example, our experiment turns out integers, then instead of little omega, we will inevitably represent an integer by a letter from the Latin alphabet in the middle portion of the alphabet, I, J, K, L, M, or N, typically. And the collection of integers is represented by tradition by an uppercase Z. Likewise, if we happen to be dealing with a real line, inevitably we describe the outcomes, the sample points. We denote them by lowercase letters at the end of the Latin alphabet. Something like X is your prototypical such letter, sometimes Y or Z, occasionally R, S, T, U, or V. And the collection of real numbers in the continuum, the real line, is denoted by an uppercase R. But to proceed, when we want to talk in abstract, we'll think of the sample space as represented by an uppercase Greek omega. Now, so much for the sample space. You should think about the experiments we have done in Tableau 3 and identify for yourself what the sample space was in each of those settings.